one of the things I like to tell people is, a lot of people come into a calculus class like this, and they're a little bit nervous. They're like, me and math, we don't get along very well. We've had a rough and rocky relationship. Well, we're here to help. And I like to say, look, this is not just about learning math. It's about learning to enjoy math. So I don't like to call these lectures. I like to call these sessions. So they're like math therapy sessions, or math therapy. So good. We're one session in, and we only have 36 more to go, I guess, after today. Now, let's talk about frustrations. There's going to be a lot of things that are going to frustrate you. And oftentimes what causes frustrations are mistakes. Where are people making the mistakes? And here is what I've discovered after working with students now for several decades, that the types of mistakes that people make in a calculus class not very often are calculus mistakes. They get the calculus part fine. The mistakes that are being made are basic things like arithmetic, algebra, things like multiplying out, factoring, expansion, making sure you know how to add fractions and work with fractions, your geometry, thinking of things, even a little bit of trig. Those are where you're going to struggle with. So if you come in here and you're like, I know my algebra and I know how to write numbers, you're in good shape. You'll do okay. If you're not, well, time to start getting better. And if you're in real trouble, we do have classes that help prepare people for calculus. And, well, hopefully that's not you. So the important thing is know your basics. Now, I also like to share this graphic for a second reason, which is if we can put a little eye here, then all of a sudden we get Pac-Man, and that's pretty good. All right. So how do we get better? All right, we'll just put this all up here at once. First thing is keep coming to class. I know it's very easy to feel like if there's no points attached to coming to class, I don't have to go. But it's really important that you make a commitment to come. Come to class. Make sure you do your homework in a timely fashion. Study for your quizzes. The basic stuff. These are the things that will determine your grade. For the homework, because of your unlimited attempts, for the quizzes, because you have the questions in advance and you have all those help hours, you can guarantee yourself a good score. And here's the amazing thing. We've looked at the data. People who do well on homeworks and quizzes pass the class almost without any problems. And you can do well on homeworks and quizzes. It's about doing the work. But you got to start early. So whether or not you pass the class is not going to be determined in 3.5 months. It's going to be determined in 3.5 weeks. Are you doing the work? Are you showing up? Are you getting the help that you need? And if you do, that's great. And let me add, we can give A's and B's to everybody. There's no quota out there. President Winterstein does not come down and say, you must fail 25%. That's not the case at all. We would love to pass everybody, but you have to earn it. You have to learn the material. And so please use the resources. Let's get up and let's just make the math department throw a party. Because we would throw a huge party if everybody got A's and B's. It would be fantastic. Do as many problems as you can. The harder they are, the better it is. And the first ones are going to be tough. It takes time because you have to learn to think. Math a lot of it is about learning to think and learning about problem solving. And so it's going to take a while to get to that point where you're comfortable. But once you do, you'll be in good shape. Ask for help. Go to help hours. It's okay to struggle. Almost sooner or later, everybody in this class is going to reach a point or they're going to see a problem and they're going to get stuck. Even if you've aced high school calculus before. I've had people who've gone through their honors high school calculus and get an F in my class because they didn't do the work. They didn't ask for help. Now, that doesn't mean that you have to have taken high school calculus to do well. I have people who haven't done that and who've done fine in the course, A's and B's, because they did the work. They weren't afraid to ask for help. The last thing is, don't be afraid of mistakes. There's a strong tendency, and And I think it's a very natural human thing, is I don't want to be wrong. And I don't want people to see me be wrong. And so I would much rather not even try than to try and make a mistake. And it's the fear of being wrong that stops you. But I want to emphasize, it's okay to be wrong if you learn from it. In fact, oftentimes we learn a lot more from a wrong answer than from a right answer, because a right answer basically just says, yeah, you know what's going on. But a wrong answer tells us, okay, we don't know what's going on, but now let's figure out why. And it shows us how we can improve. And this is how you make progress. You try something. And then if that doesn't work, you try something else. And you keep going. The important thing is to not give up. Which is, you'll see here, a wrong answer can be more beneficial. All right. Now, that's it for advice. Really, this is real calculus now. What is calculus about? Here's my very short course on calculus. So, calculus is a beautiful subject, and it comes from sort of resolving two issues. The first thing is the fact that we understand things which are flat. We understand flat things well. And when I say a flat thing, like a line, that's flat. A rectangle, a box, or in 3 dimensions what we call a plane. These are all flat objects. These are things which we can understand. The problem is that the world around us is not flat. We don't see straight lines. We see wiggly lines. We don't see rectangles. We see 2-dimensional blobs. Instead of boxes, some sort of bean shape. And instead of a flat plane, some sort of curved surface. Things aren't flat. So the things which we're good at are not the things which we have to deal with. So here's what calculus does. It says we're going to approximate things that are not flat by things that are flat. And that's the idea. We can use our understanding of how things are a flat object, and then we can lift that up to help us understand things which are not flat. So we're going to start by one of our favorite flat things. In fact, I'll probably say it's our absolute favorite flat thing to work with. And it's lines. So lines are our favorite flat thing. Because we understand a line. It's really easy for us. You know, we just draw ourselves a space and we just shoop, we have ourselves a line. So let's just recall a couple of things. So there's a couple of forms for an equation of a line. Well, one equation for a line, that's one of the ones that people think about, is called slope-intercept form, where m is the slope and b is your intercept, where you hit the y-axis. So I've marked b here. Now, of course, what do we mean by slope? So that's our m. So slope is a measurement of something. More or less, you can think of it as how tilted is my line. Because as my slope varies, my line is going to move around. So the way it's measured, it's a ratio. It says, I'm going between a pair of coordinates, x1, y1, x2, y2. I can look at how am I changing in the x direction, how am I changing in the y direction, and I compare the two. So it's sometimes called the rise over run, or the change in y over change in x. So if you see a capital delta, that usually stands for a change in this variable. So how are these variables changing with respect to one another? So what are slopes? They're measuring rates of change. In particular, how our y changes as we change our x. So this is important to understand. Slopes are rates of change. When I see a positive slope, what does that mean? It's a positive rate of change. Now, in terms of the picture, a positive slope, we interpret it as going uphill. What that tells us is that as we change x, y is changing in the same amount. Or rather, not the same amount, but in the same direction. So in other words, if my x goes up, my y goes up. Now, a negative slope is a negative rate of change. And that we oftentimes think of as a line that goes downhill. But what that says is if my x goes up, my y actually goes down. So that they now move in opposite directions. As I'm increasing my x, my y is decreasing. Now, zero slope just says, look, if I change x, then there's no change in y. It's flat. It's staying level. And 0 is going to be an important slope as we go on later in the course. So let's do an example. Find the line passing through the following points. Now, I haven't put anything. This is your choice. What points do you want? So someone give me some numbers. Anyone? 6. We've had a 6. We need more numbers. 8. And there was a 17 in the back. 4. Now, they don't all have to be positive. You could have made some of them negative, but that's okay. So what we have is we have 2 points. 6, 8, 17, 4. And I want to find an equation for the line that passes through these 2 points. Well, how can we do it? There's a couple ways. There's not one single way. But oftentimes I like to do it by first off finding the slope. So the slope is going to be my change in y over my change in x. So for change in y, I say, okay, if I'm going from 6, 8 and ending at 17, 4, I started at 8, I ended at 4. So that says I went from 8 and, I take 4, subtract 8, because what's the difference? 4 minus 8. For change in x, I start at 6, I end at 17. The difference is 17 minus 6. So we'll end up with negative 4 11ths. Okay, well, that's my slope. No, that's not a line. But we're really close because there's a nice form. Now, there's slope-intercept, and there's another form called slope point. Y minus some y value is m, x minus some x value, where y naught and x naught, that would give us a point, and m would give us a slope. Now, the question is, which point do we choose? Do we either choose the 6, 8, or do we pick the 17, 4? If we want to get the right answer, which one do we need to pick? Yeah, it doesn't matter. Yeah, good, good. You're catching on. Okay, sometimes there's more than one right way to do things. So, in our case, I'll just pick the 6, 8. Y minus the y coordinate, 8, is equal to m, negative 4 11ths, x minus the x coordinate. Well, that's 6. Just make sure you always stick with the same point. You don't want to mix and match. And that's it. We're done. Now you might say, well, wait a second. Don't we have to simplify? Because I had high school teachers and they were very much about simplifying. And the answer is, if we don't tell you to simplify, you don't have to. Because this is not what the goal of the class is. The goal of the class is not to learn about simplification. It's to learn about math, intuition, much more important. All right. So we've got a handle on lines. Good. So let's get into our goal. Differential calculus. This is the major topic of the course, and probably what we'll cover in about the first 70% of the course. It asks the basic question, how is something changing? What is the rate of change? Now, we know how to answer that for one special case. And that one special case is what we just talked about. For lines, they're our favorite things because we know what the rate of change is. It's the slope. So we do know how to answer it in at least one case. But maybe we don't have a line. Okay, well, what do we have? Well, maybe we have our coordinate system here. We'll draw that. And we have something which is not flat. All right, so maybe that's what our function is doing. And now we ask the question, what is the rate of change? The correct answer is, it depends. There's not one rate of change, because we can see there are places where our function is going up. That's a positive rate of change. We can see there are places where it's going down. That would be a negative rate of change. So there's not one rate of change. But we can do the following. We can say, what's the rate of change right there? What's going on at that point? All right, well, good. Now that's a little bit harder, because we can't sort of cheat. Okay, well, let's think about what we can do. Well, we go and we zoom in. It's like we pull out our magnifying glass. So if we zoom in, what will we see? Well, we're going to see that. We say, okay, notice that when we zoom in, we focus in, it's a little bit cleaner. There's not quite as much movement up and down. But of course, there's still some, so it's not really fully refined. So it's like, okay, well, instead of a magnifying glass, let's pull out our microscope. Microscope. Okay, now we're zooming in. Okay, and as we zoom in, it looks even more flat. All right, but it's not perfectly flat, but it's more flat. All right, well, what can we do? Well, we'll go into one of these science buildings. They've got money. And we'll get their like scanning electron microscope. We'll zoom in super, super close. And what are we going to see when we zoom in super, super close? It's going to be so flat, it's imperceptibly different from a line. We can't distinguish it from a line. This looks flat. So the key here is close up, this becomes flat. And now we say, okay, if it's flat, that means it looks like a line. And we say, perfect. We know what to do with lines. For lines, we talk about slopes. So to answer the question, how is something changing, what we're really going to do is we're going to say, okay, what does it locally look like? It locally looks like a line. What can we say about that line? What can we say about the slope of that line? That's our goal. That's our goal. Now, how are we going to get there? It's going to take us a couple days. But we want to find the slope of that zoomed in line. But the way we're going to start is by saying, okay, let's look at not zooming in all the way, but let's just sort of suppose I look at what's called an average rate of change. So I have the 2 points. In fact, we can see the picture here. I have A and B. And I want to ask the question, what's the average rate of change from A to B? Okay, well, what does that mean? Well, the way we're going to interpret it is we say, well, look, there's a point in the function, A, f of A. There's another point in the function, B, f of B. And imagine we draw this line. It's called a secant line. Now, secant is designed to cross. It crosses at multiple points. So I have this secant line. And I want to ask the question, what's the average rate of change? Well, it's going to be the change of the output, f of b minus f of a. So it's this length here, f of b minus f of a, over the change in the inputs over b minus a. In other words, how much did y change versus how much did x change? Now you're probably thinking, this sounds really familiar. Change in y over change in x. It sounds a lot like the slope of a line, because it is the slope of a line. It's that slope of the secant line. So the average rate of change is the slope of a secant line. All right. Well, let's test it. So let's find the average rate of change for y equals 5x plus 219 from x equals pi to the 5th to x equals e to the 17th. Now, you might be a little bit suspicious that these numbers look really, really bad. Now, if you see numbers that look really, really bad, you should think, maybe there's a better way to do it. All right. Can you see, is there an easy way for us to figure out what the average rate of change is for this function? We have some people saying it's 5. Okay, that is correct. How did you do that? Yeah, see what's happening is this is not just any function, this is a line. And we understand what's happening with lines because they're our favorite thing. They're flat. And so if I want to understand what's that rate of the change, well, it's like a slope because we said it's that slope of that secant line. Well, the secant line is just the line. So it's very easy to find the average rate of change. So, okay, well, that wasn't so bad. We should do something a little bit more challenging. All right, find the average rate of change for y equals something from x equals something to x equals something. Now, in the interest of time, I'm going a little bit slow. I'll just make up a function. X cubed plus 2e to the x from x equals 0 to x equals 2. There we go. Something easy. Well, how do you find it? The answer is you use the formula. It's a really good formula. So if I want to know the average rate of change, it would be f of 2 minus f at 0 over 2 minus 0. On a side note, what if you made a mistake and you put f of 0 minus f of 2 over 0 minus 2? It'll be the same. Because what you're really looking at is you're looking at differences. And as long as you flip both differences, essentially when you're flipping something like this, it's a change of orientation. So two changes in orientation cancel each other out. So don't worry about which one's larger, which one's smaller. The formula has it built in. It can handle either order. So f of 2 minus f of 0 over 2 minus 0. So what do? Well, you plug in 2. You get 2 cubed plus 2e squared. That's f of 2. F of 0, 0 cubed plus 2e to the 0. And then over 2 minus 0. Now you could simplify that a little bit. I think this one's okay to simplify. Here you're going to get 8. But then you're going to get a minus 2. The 0 goes away. So you get 6. Then you get plus 2e squared divided by 2. Or you get 3 plus e squared. So, So yeah, it's finding an average rate of change. If you know the function, you know the points. It comes down to plug in the formula, see where you go. Now, what's our big idea? Well, we know to talk about these secant lines. I can find an average rate of change for a secant line. That's pretty straightforward. We're going to look for something called a tangent line. Now, a tangent line, the idea of secant is I'm going to cross. The idea of tangent is I'm going to touch. So I'm only going to touch at one point. That's the idea. So secant lines are fairly easy to figure out because I have 2 points to work with. And 2 points, I can get a line. Tangent lines are trickier because I only get 1 point to work with. 1 point is not enough to make a line. But here's the idea. So I have this point A, and I want to find this tangent line. It's marked solid red line. And I say, well, look, what I can do is I can go to a nearby point and get a second point at B and make a secant line. Now, if I'm far away, it's not a very good approximation. You'll see that this dotted line here is not a very good approximation to that red line. But that's okay. What do? Move a little bit closer. It gets a little bit better. Move even closer, and it gets even better. And where do we stop? Well, the thing is, if we stop, it's only going to be an approximation. We want to go and get the line, not get an approximation to the line. So we want to keep getting closer and closer. All right. So let's do an example. Find the tangent line to a parabola. Okay, so parabola, it's a second order polynomial. All right, does anyone have a nice parabola? X squared plus 2x? I think somebody said. If not, I'm going to write it down anyways. And now, to find a line, we also need to know a location. What value of x? 3 is the first number I heard. Now, I know that you probably can be like, I know how to find this tangent line really easy because I took calculus before. Bear with us. Give us a couple days. We'll get there with you. Okay, so what do we need? Well, to get a line, I need to get a point and a slope. Now, the point is fairly easy because I have the x-coordinate. So for my point, I say, all right, take 3, plug it in. 9 plus 6 makes 15. So the point's not so bad. Now what we're going to do is we're going to say, okay, our A is 3. Then we have this B that's going to get closer and closer. Now I'm not going to really set B to anything right now. I'm just going to keep B as a variable. But I'm going to look, if we call this here f of x, I'm going to look at my f of B minus f of 3 over B minus 3. So in other words, I'm finding the average rate of change, which is, again, that's the slope of the secant line. So I'm finding the average rate of change between B and 3. Now, this becomes, well, B squared plus 2B, or is it not 2B? No, it is 2B. Yeah, all right. So that's when I plug in B. Everywhere I see an x, I'm replacing it by B. f of 3 we already computed as 15. And then we have b minus 3. Now, what do we want to happen? Well, of course, we want to plug in b equals 3, but that's kind of weird because I see a b minus 3 downstairs. Now, b squared plus 2b minus 15, if we're lucky, what should be true? It would factor. Are we lucky? I hope so, because otherwise there's a big problem in math. And that would be bad to start on day one with a big problem in math. What does it factor as? Does anybody know? b minus 3, b plus 5. Now what can we do? Well, we cancel off the b minus 3's. Now here we can cancel because we really are never going to set b equal to 3. b can be anything, but it can't be 3. So, for any secant line, I would have a slope of b plus 5. Now the question is, well, which secant line do I want? Well, I want to get the secant line when I let b get closer and closer to 3. So what's happening to b plus 5 as we get closer and closer to 3? It goes to 8. So that secant line here, it's swinging in, and the slope of the secant line is going to approach the slope of the tangent line, and so that is going to be 8. So that's our slope. We have our point. Here's our slope. So we say y minus 15 is equal to 8x minus 3. There's our tangent line. All right. Well, one tangent line down, many to go. Okay, let's do one last example. So suppose we're given the following information. F of 1 is equal to 3, f of 9 is 11, and that the average rate of change of f of x between 1 and 4 is twice the average rate of change of f of x from 4 to 9. Then what is f of 4? So let's see if we can parse this. We're trying to understand something. We know our goal. Our goal is to find f of 4. And so we're going to take these statements and translate them and write them as algebraic expressions. So let's do this first statement. The average rate of change of f of x from 1 to 4. So that would be f of 4 minus f of 1 over 4 minus 1. The average rate of change between 1 and 4 is secret code for equals. Twice is secret code for the number 2. The average rate of change of f of x from 4 to 9. Okay, so that's f of 9 minus f of 4 divided by 9 minus 4. All right, so literally we just take the statement and write it down. Write down what it means in math and algebra. Okay, now I'm not a big fan of fractions. They challenge me. So usually when I see something involving fractions, I say, let's get rid of the fractions. Now in this case, I want to get rid of the denominators. So here I have a 3, 4 minus 1. Over here, it's 5. So I'm going to multiply both sides by 5, and I'm going to multiply both sides by 3. And, well, actually before we do that, let's substitute what we know. We know f of 1, that's 3, so this part is going to become 3. And we know f of 9, that's 11. So that part becomes 11. So, updating. F of 4 minus 3 over 3 is equal to 2 times 11 minus f of 4 over 5. Now, clear the numbers, as we just said. Then we will get the following. 5 times f of 4 minus 3. I got too excited. Too many parentheses. Okay, compensate. All right, now we're okay. We're balanced out. Is equal to 6 times 11 minus f of 4. This also goes by the name of cross multiplying, clearing your denominators. Multiply through. 5 times f of 4 minus 15 is equal to 66 minus 6 f of 4. Now we can move this around. We'll add 15 to both sides, add 6f of 4 to both sides, and that'll give us 11 times f of 4 is equal to 66 plus 15. Well, that's 81. And so we can conclude f of 4 has to be 81 over 11. Exactly what we guessed when we started. Wait, no, it wasn't. We didn't guess that. We had to do the work. But that's okay, because we know how to do the work. We read through the statement, we translated it, said, okay, how do we translate this sentence to a formula? All right, use what we know, simplify, clean it up, clean it up, clean it up, get our answer. And we're done. Life is good. Life is good. All right, good. Okay, so hopefully we're all here for Calc 1. That's what I'm going to talk about. It's a great class, and we'll have a lot of fun. Now, normally I'm going to start with sort of a review question, but we don't have anything to review because it's the first class. So I thought I'd start with a different type of question. So suppose you have a deck of cards, and you want to ask the question, how many times should you shuffle a deck to be random? So here's a deck of cards. You can buy a deck like this at many places. There's usually a couple of extra cards. We don't need those. Okay, so here we go. Here's a deck of cards, and it comes in a fairly nice order. So if you've ever opened up a deck of cards, you see it comes in a nice order. You've got all your hearts, you got your clubs, you got your diamonds, and you got your spades. Now, of course, we put it in this order so that you can open a deck, quickly check, and verify all 52 cards are there. No duplicates, they're all there. But you won't want to play with these cards, because now you know the order of the cards. You can always predict what card comes next. Games aren't fun anymore. So we got to mix them up. So that's what we mean by random. You want to play a game. So the question is, well, how many times should you shuffle? We know the answer is definitely not 0. Okay, well, here are some choices. This one's easy, multiple choice. 1, 4, 7, 8, none of the above. Maybe you can never shuffle enough to be truly random. Well, of course, there's a great question. What does it mean to be random? So let's just let's do an experiment. Okay, so here we go. One shuffle. Is it random after one shuffle? What do you think? No. Yeah, you've played games before. Okay, good. Now, if you're not convinced, if you take a look at the cards, what you'll see is that all the black cards are together, all the red cards are together, not very random. They should somehow be better mixed. Okay. So we know it's not 1, but then the question becomes, well, how many do you need? And is there an answer? I mean, do we have to just keep shuffling forever? And these are important questions. So they're actually very, very important questions. Say you might own a casino. And you're like, well, look, I don't want people to have an advantage if they're going to come play cards in my casino. And so you want to shuffle for enough. But you don't want to shuffle too much because you do want to play the game. If you spend 2 hours shuffling, it's not very much fun. All right. Well, so our next stop was at 4 shuffles, where we just finished 3. So here we go for shuffle number 4. Now, I do want to assure you, this is a normal deck, and there's only one. Look, we're math professor salary, you can only afford one deck. So we can't afford a second deck. All right, so here you go, 4 shuffles. What do you think? Random? Hard to say, hard to say. But, you know, I should say normally it's hard to say, but I will say that this particular deck has a nice built-in feature, which is if I look at one particular side, I can check, no, it's not random yet. Okay, got to keep going. Turns out if you only do 4 shuffles, it's not enough to make it random. Now, when I say random, I really mean to say, look, you haven't lost information. So if you knew the order of the cards at the start, and you knew that there were only 4 shuffles, you get a little bit of an advantage. Now, the more shuffles you do, the more the advantage disappears. So these are mathematical questions, and mathematicians have answered them. One mathematician in particular, his name is Percy Diaconis. He started out life as a magician, but he wanted to get good at gambling because he wanted to beat the other poker players. So he said, all right, I'm going to run away from math. and run to graduate school. Went, studied mathematics, got his PhD, now teaches at Stanford University. And he says, lo and behold, 7 shuffles. If you shuffle a deck 7 times, it's very random. By which, basically, you're not going to be able to predict the next card any better than just random guess. You've lost information after 7 shuffles. So the answer is 7. However, I like my decks like I like my math exams. Extra random. So I'm going to go ahead and do one more shuffle, an 8th shuffle. Now, if I have a random deck and I do a shuffle to a random deck, what's going to happen? Well, it's going to be random, right? And you can't unrandomize. And so now, here we have a very extra random deck. Now, you might be suspicious. You say, wait a second, you started with the ace of spades and you still left with the ace of spades. Look, something's got to be on top. Don't read too much into it. I'm sure that once we see the cards spread out, that we will see that this is, in fact, a very nice random ordering. Okay, so you should always shuffle your deck 7 times, but apparently not 8. All right, that's okay. That was our question for today.